All right, titration, acid-base titration. Now, you've done the strong titration before, so we're going to briefly review that, but we're also going to be looking at the titration points along the curve and the different things happening along the curve. So we'll be looking at our different spots along, and we'll also be looking at what a titration of a weak with a strong, like a weak acid with a strong base, or a weak base with a strong acid, how those particular curves have a tendency to look. So basically for a titration, reviewing that you have a standardized solution, which is the titrant, the one that you know the concentration, it's the one in the buret, the one that you will be adding to the flask, like you did in the KSP of calcium hydroxide. That was the 0.10 molar of the hydrochloric acid. That case was the titrant. It was in the buret. That's what you had the known concentration. You were adding it slowly to your calcium hydroxide solution that was in the flask. The Analyte was the calcium hydroxide solution. You didn't know its concentration. You did know its volume. You put 30 milliliters in there. So in that particular example, you knew the volume of the Analyte, but you didn't know its concentration. You were going to use the stoichiometry once you reached your equivalence point and be able to figure out the moles of both the moles of the base of the calcium hydroxide and then divide it by its volume to get its original concentration. So that was one lab where we just basically neutralized it, did the equivalence point, calculated the KSP from that concentration. Now we're going to, like I said, go along the curve and calculate the pHs at different points along the titration curve, and also look at similarities and differences among the strong combo versus the weak strong combo. Strong's easier, weak strong's a little more difficult. So keep that in mind when you're looking here. So hopefully you got what the titration is, what is the titrant, and the Analyte. Okay. Now we're going to look at the net ionics again, review some of those. Going back over them, they're from like Unit 1 where we did some net ionics for titrations. So for a strong acid, strong base combo, this particular example is showing you hydrochloric, the strong acid with the strong base, sodium hydroxide. And if you you break them apart into their ions, you would break this apart, H plus, Cl minus, and A plus, OH minus. The water stays together, remember, because it's a liquid. And then this, of course, would break apart too, because it's a soluble salt. And this would be the complete ionic equation, the one that I just drew in green. Remembering that these guys are spectators, so they don't appear in the net ionic equation. So we get rid of them for the net ionic equation. They get canceled out, and what's left over, things doing the actual reacting, which would be the hydrogen ion, the hydroxide, forming the water. So those are the only things you would actually include into the net ionic equation. Little review from Unit 1. So the green step, where I drew in the green there, that's the complete ionic, where you break everything up into its ions. You leave solids and liquids and gases together, of course. Anything AQ, though, that's soluble or that breaks apart or ionizes like the acid does and the base does, you would separate them. And remember, strong acids and strong bases completely dissociate or completely ionize, so they're going to always separate. And you would cancel out the spectators, in this case sodium and chloride are both spectating ions, not participating in the reaction, and you end up with your net of just hydrogen plus hydroxide giving you water. Strong is always going to be that particular net ionic. The other ones should always cancel out. This other elements that are in the salt will always cancel out for a strong combo. However, here, if we're looking at our strong base weak acid titration problem, we're looking at the net ionic here. You would remember too that the sodium hydroxide would break apart, so you'd have your Na plus OH minus here. Because acetic acid, that's acetic acid or vinegar, it is a weak acid. It only partially dissociates. It would need to stay together. Of course, the water is a liquid, so it stays together. And then, of course, here we have sodium acetate. And the sodium acetate is a soluble salt. Remember, all acetates, this is where the solubility rules, you got to remember those. And alkali metals are always soluble as well. So this one would also break apart into the ions. But then, as you see, there's only one spectator in this case, which would be the sodium. The sodium's the only one spectating. Everything else would have to remain in the net ionic equation. So you would have your hydroxide left over from here, reacting with the acetic acid to give you the water, and then you also have the conjugate floating around in there, that conjugate base, the acetate. So in this particular case, a strong base with a weak acid, it ends up only having one spectator, which happens to be sodium. And weak acids, weak bases, you must keep together because they only partially dissociate, so we don't separate them in the equation when we're writing out the chemical reaction equation. Any questions on that? Once again, this is kind of a review from Unit 1, but you can go back to your reactions packet too. Yes? In this particular case, because it's neutralization, no, it's going to completion. So the hydroxide here will pull off the H, will form water, because it is neutralization. This is actually a reaction. Double arrow, like what we were doing before the break, the double arrow one was actually the acid or base reacting with water. That does establish an equilibrium. Here, you're not really establishing an equilibrium. You're doing full-out neutralization. It's a very good question. So there is a difference because we are not having the acid or the base react with water itself. Here is actually the acid and base reacting together to create water. So it is a full-out reaction, not an equilibrium position where only partially reacts with water, producing some ions. So for every hydroxide, it's going to pull off the H off of the acetic acid, and it's going to create one water, and it's going to create an acetate floating around. So that's a good question. Okay, so here's one showing a weak base with a strong acid, where you have ammonia reacting with hydrochloric acid. Okay, once again, this would break apart because it's strong, so it breaks apart into its ions. And this is more of a Bronsted-Lowry reaction, obviously, because the H donates over, creating your ammonia. But you would have chlorides on both sides, so those chlorides are spectators and do get canceled out. So the net is only going to really be the ammonia itself reacting with the hydrogen, creating ammonia. So once again, if you see two ions on either side of the arrow here, it's going to end up being a spectator and gets canceled out here. And our hydrochloric will donate that H over to the ammonia, creating ammonium. Any questions on that? So this is one particular one where they're showing the weak base strong acid deal, and ammonia being one of the weak bases. And I said those other, you can identify other weak bases because they'll have amino groups on there, the NH2 groups. However, you know, for your insoluble hydroxides that are very weak bases like magnesium hydroxide, so remember your strong bases are going to be the alkali metals with hydroxide, or calcium, strontium, barium with hydroxide. So magnesium is not considered a strong hydroxide, but you can react it with hydrochloric as a solid, and it will neutralize the hydroxide into water, and you will end up with the chlorides being spectators. See, they're both in their ion forms on both sides of the equation. However, since you're starting with the magnesium hydroxide solid, it's very insoluble, remember, then you would end up with magnesium ion and your water on the other side. So this particular case is showing you another weak base strong acid where the weak base happens to be a solid hydroxide, metal hydroxide, that is insoluble. Because most of your hydroxides, besides the strong ones, are going to be insoluble on the solubility rules. And they're going to have very, small KSPs. Okay, so that's just an example showing you that kind of reaction as well if you were to see one like that. Most of the ones you're going to see, though, are going to be the soluble ones that have the amino groups, the NH2 groups on them, or it'll be something with ammonia in it. But once again, spectators cross out. We only want what's reacting in the overall equation to get your net ionic. Now for the curves. Titration curve, of course, is the plot of the pH of the analyte as the standard solution is being added. So in this particular example, it's showing the titration of hydrochloric with a standardized sodium hydroxide. So your unknown, or the analyte, is the hydrochloric. The titrant, or the known one, is your sodium hydroxide. Slowly adding the sodium hydroxide, you see over here, you do have the slight increase in the pH, and then you eventually reach this inflection point. The inflection point where it dramatically increases. You see that up and down, giving you that S-shaped curve. Okay? That, of course, is going to end up being where you're going to find your equivalence point. And then on there, as you can see for this particular reaction, showing you where like the bromothymol blue and the phenolphthalein, those indicators would change at those different pHs, and use indicators to figure out the equivalence point because their endpoint should change color around the equivalence point if you're picking the correct indicator to go with your particular titration. Don't forget that we're talking about the equivalence point, that's talking about the stoichiometric point, not when the color changes. The stoichiometric point is when the moles of the acid, or H+, equals the moles of the hydroxide, the OH-. We'll talk about the endpoint in a minute. If you pick a good indicator, your endpoint should be at your equivalence point. If you pick the wrong indicator, though, the endpoint may not be at the equivalence point of your reaction. So you add enough to where the moles equal the moles. That's the important part if you're reaching that equivalence point. So let's take a look and look specifically at a strong curve here. All right, this one was showing you a strong base with a strong acid titration. So this one is a strong base with a strong acid. And what you should just basically draw in there, you don't have to be as detailed. You could just put, like acid over here, pH 14. But what you should notice, this is very important right here, the pH at the equivalence point for a strong is going to be at 7. So this part is important, 7. The pH at the equivalence point when you've added enough of the titrant, your equivalence point should be at 7 if they're both in the strong category. Must be strong acid and strong base. So it has to be one of your 7 acids. That's hydrochloric, hydrobromic, hydroiodic, perchloric, chloric, nitric, and sulfuric. So any of those, and then your strong bases, which are going to be your alkali hydroxides and calcium, strontium, barium hydroxide. Although we know the heavy metal hydroxides in group 2 are slightly soluble and they do have KSP values. Obviously, when you did the KSP of calcium hydroxide, you noticed it had a KSP value that was like 10 to the minus 6. So it's in the slightly soluble category, but it does create a high level of pH. So assuming even though it doesn't completely dissociate when it dissolves in water, it's slightly soluble, but because it does provide a high pH level, they classify it in the strong base category. Okay, now for looking at a strong acid with a strong base. So in this case, you had the reverse S. Now you have the regular S shaped, kind of like the first one I showed you. But you do need to, of course, mentally note, since we've already noted it, that the equivalence point is 7. Strong, strong, always 7. Now, in here, the equivalence point should equal the endpoint of the titration, and the equivalence point is showing you the inflection here on the graph. It has like that huge, dramatic either increase or decrease. For the acid being titrated with the base, it's going to be an increase in pH. For the base being titrated with the acid, it was a decrease in pH, the reverse S. Okay, so that inflection of the curve is important. That's where you're going to be looking for that equivalence point. And also, if you weren't able to use a probe in order to detect the pH, you would use an indicator and it would change color, and that would be what the graph would look like at that point. So strong acid, strong base. This time it looks like the regular S. If it's strong base with strong acid, it's the reverse S. But both have a pH of 7 at the equivalence point. So like I said, noting exactly how much is added down here, isn't necessary, but the general idea of what the graph looks like and those important marker points on it are necessary. So pH of 7 at the equivalence point. We'll talk about the endpoints here in just a second because we're going to get to the indicators. Okay. So, endpoint of the titration marks when the indicator changes color. So the equivalence point is not necessarily the same as the endpoint, but if you're doing your titration correctly, you're choosing an indicator that's going to have a color change around your equivalence point, or it will give you bad data. And you won't get the correct concentration of your unknown. So you will be selecting, like we selected I selected the bromothionyl blue for the KSP of calcium hydroxide lab because I knew it was a strong acid with a strong base, so the pH of the equivalence point should be 7. So I picked bromothionyl blue because it changes from, blue to green to yellow right around 7. And you want to pick one that will change that at that equivalence point, so you know the when the moles have equaled the moles, and you know when to stop adding more. Now, having the pH probes and being able to plot the graph is very nice, especially if they work better, but you can use just the indicator changing color and do the calculations and the stoichiometry from the amount of volume added of your known to figure out your concentration of your unknown. We did those problems in Unit 1, the strong titration, neutralization problems. So they're very similar to those. Okay, so this is endpoint again, marks when the indicator changes color. Indicator changing color, you want to pick it to be close to your equivalence point. So like here, this particular indicator is called phenolphthalein, and it is clear. This is clear when it's an acid, and it turns a hot pink color when it's base. Usually changes around like a pH of 8, I believe. So really, as you can see down here, they have these complex chemical structures. They're big organic molecules, the indicators are, but it's a matter of whether they have the H's or the OH's on them. So they change color. So when they are fully hydrogenated with H's, this is when it's clear. If they pull them off, then it turns pink color. And that's kind of how the indicator works. That's why you don't add very much to it, just enough to see the change, and then it doesn't too overtly affect your results. But it does tell you when you're reaching your equivalence point. So phenolphthalein is one that we use a lot, just really for a generalized acid-base. Is it an acid or base for the solution? The methyl orange indicator is yellow in basic solution and red in acidic. Although here, I know it looks kind of more like orangey color, but really they call that yellow. So kind of get an idea here of, so methyl orange is an indicator that can be used. And then you have the red when it turns into the base over here. That's another particular one I'm going to show you. You can Google charts with indicators. There are so many out there with various ranges of their color change. Here's the bromothymol blue one that we used in the KSP of calcium hydroxide lab, and you can see it turns green kind of right around the 7 there, right around the 7 mark, and blue just slightly above 7. That one's a good indicator for ones that have changes right around where their equivalence points are right around 7, the strong cases. So the bromothymol blue is a good one that we like to use in those particular cases. But as you can see here, this is just one particular chart I found. There are so many indicators, and it shows you their colors and their changes. So if we're looking here at something like this cresylphthalein, this one's like clear, and then it goes into the hot pink, but it's changing like right around 9. Really changing over. You have this one's at the lower end of the pH scale here to the cresyl red. And then here's that methyl red showing you, right, it was methyl orange, and yeah, methyl orange here. Although it looks like the change is right around 4, becoming more basic. Bromothymol blue here, showing you the pH change of the green at the 7 mark there. Phenol red is yellow over here in acidic, and red. Okay, so lots of different indicators that you can choose from, but you want to pick the one where its change is occurring at the equivalence point, and you would have an idea of where your equivalence point is going to be based on what you're titrating. Okay, so looking here, we're going into checking out now how the titration curves look for a weak strong combination. And this one's a weak acid being titrated by a strong base. There's going to be noticeable differences on the graph that you'll need to make sure that you take note of, and that you will be able to identify very quickly in, say, a multiple choice problem or free response problem. The first thing that you should notice, and you would be able to tell that this is a weak strong, is that weak acid titrated by a strong base. The equivalence point is above 7. Okay, so it's noticeably up here above 7. That's one aspect of the weak acid being titrated by the strong base. The next one is there is something called a buffer region on this particular titration graph. The buffer region is basically from the place where you start adding, not at 0, but once you start adding hydroxide, all the way to the equivalence point. This area is known as the buffer region. And we will have buffer solution at that point. You don't know what that means yet, but we will be talking about the components of the buffer solution later on in these lecture notes. The next thing is there is a half equivalence point that we pay attention to. I'm going to tell you why in just a second. The half equivalence point is the midpoint of the buffer region, to be halfway to the equivalence point. The reason why that's important here is because we have an actual numerical value that translates to the pH of that, and that numerical value is where the pKa equals the pH. So at that midpoint, the pKa equals the pH. And once again, I've said this before, I'm not sure everybody caught it, but when you put P in front of something like that, pKa, that's really all you're doing is taking the negative log of that value. And so the negative log of the Ka equals the pH at the midpoint of the buffer region. So, noticeable characteristic differences here when we have a weak acid being titrated by a strong base. Any questions? So now we're going to look at a weak base being titrated by a strong acid, because it's also going to look different. So of course, the first thing you should notice here is the equivalence point. It's not above 7, it's not at 7, it's actually now below 7. That's an important thing to note here. On this particular graph, an example, this is showing the ammonia being titrated by hydrochloric acid. You see that the pH at the equivalence point is 5.3. So that's definitely lower than 7. Still has the opposite S curve as, say, a regular strong would. But we also have a buffer region. Okay, the buffer region starts up here, goes to the equivalence point, this whole area of the buffer region on the weak base being titrated by the strong acid. The problem is, though, its titration curves are measured by volume and pH numbers. So this is where it's a little bit backwards when you're titrating the weak base with the strong acid. The midpoint of the buffer region, since it's measured in pH, is going to be the pKa of the conjugate acid. So you'd have to look at ammonium's Ka, then you do the negative log of that, you can get the pH at the midpoint there. So we want to look here, we'll be looking at the conjugate acid, its Ka value, and a lot of times when you have a base problem, they're going to give you the Kb. So what would you do in order to find the Ka?
1 times 7.
So you would want to use your Kw equals the Ka times Kb thing. So if they gave you this problem where they gave you the base, they gave you the Kb, but you needed to find the pH at the midpoint, one option is to use that formula, find the Ka, do the negative log. You do have another option, but this is definitely, same idea, but different way of working it. You could look at the pOH. You would do 14 minus the pH, of course. If you do the negative log of the Kv, that would give you the pOH. You subtract that from 14, then you can get the pH. So you can do it that way as well. Another option. finding the POH from the PKV. The POH equals the PKV at the midpoint there. But then you have to do the extra added step of subtracting it from 14 to get that pH value. Because these titration curves are never going to be measured in POH. They're always going to have the pH on the Y value or Y axis. Does that make sense? Any questions? All right. Now let's look at a diprotic example here. Okay. Since we have two H's and we know that this occurs in two steps, right? The neutralization is always going to produce water as a product. So here I'm going to go ahead and give you generic that you can look at. So if we had H2A plus our hydroxide, that's going to give us the water and our conjugate base there. So this one, would be for your PK1. And what you would have to do is you would add hydroxide and you would neutralize the first H. So that's this part of the curve. Going through here, getting through the neutralization. Now, these diprotic ones that you would be looking at for this particular example would be ones that are weak diprotic acids, something like oxalic or, carbonic, stuff like that would be considered in this realm. Now, once again, the midpoint of the buffer region here, okay, that's going to be the negative log of the K1, which would be taking off the first hydrogen. Then you would reach your equivalence point somewhere in here. And since this is an acid being titrated by hopefully a strong base here, you would notice that equivalence point should, be a little bit above 7, but you're going to see these, the pH values continue to go up. Now the second part over here, this part of the curve, that's going to be to take off the second H. So you would start with the conjugate. Conjugate would start that particular one. You're still going to get water as a product, and then you would have the conjugate base A minus 2 because you took off both H's there. Okay, this is going to give you your, PK2 equals the pH at the midpoint. This one equals the pH at the midpoint of the first curve. The PK2 is going to equal the pH, which is the midpoint of the second curve of that buffer region. So this is, buffer region 2. You have 2 buffer regions going on, but they're not going to have you work through lots of the math with these. What they will do probably is give you the graph, and then they'll be asking, like, at this point of the curve, which species is the most abundant in solution? Like, they asked you, like, right here, they put, say this is point A, which species is going to be the most abundant at that particular part of the curve? Anybody know? Right there where I marked A. HA minus. Why HA minus? That is true, but why? Good, yes. So at this point, all of the H2A has been changed over into HA minus because we've already gone to that equivalence point and it's already been changed over. He is correct. So now we're starting out with HA. We've added a little bit of hydroxide because we're already in the buffer region. So that means we have mostly HA minus, but there's a little bit of A minus 2 there at this point. That makes sense because a little bit has been neutralized. Now, they could ask you at this point too, like right here. right at the, in this second equivalence point here. What would be the major species there at that particular one? Right at that second equivalence point. A2 minus would be the thing that's in there. That would be the most abundant because all of the HA minus has been neutralized. You haven't put any more hydroxide in there. And so pretty much you just have the second conjugate there, second conjugate base. Then of course they could ask you, like, at this point, all the way up here, which species is the most abundant? Now at that point, it's going to be what? What have you added a lot more of? The hydroxide. So at that point, you have excess hydroxide sitting in there. Yeah. So that's kind of the questions that they'll ask about, say, a diprotic curve or a triprotic. What is the difference, though, between a diprotic and a triprotic, do you think? So this is what the triprotic one's going to look like. You have 3 curves on it, 3 midpoints, 3 pKa's that will give you the pH of the midpoints. It's 3 steps now. And of course, something that's triprotic is going to look like phosphorus or phosphoric, something like that. There aren't a whole lot of triprotic acids out there, but as you can see, it's going to kind of follow the same idea as the diprotic curve, except for you just have one more to neutralize. You have a 3rd step, you have a 3rd Ka. Any questions on that? There is one other thing I do want to point out that I didn't address in the diprotic one, but at each midpoint here, and this goes for all of the weak, strong combinations, right at the midpoint, your original acid amount and its conjugate are at equal concentration. And that is why you can do the negative log of the pKa, or negative log of the Ka, and get the pH there, do the pKa. Because those concentrations of the original acid and its conjugate are equal, that's why that numerical value actually works. So you'll notice too at the second midpoint here, now you have the conjugate of the first is now the reactant, so that is now equal to its conjugate. And then the next one here, right at that midpoint, those concentrations are going to be equal. So that's why you can do the pKa of that particular Ka value for that step, and it will give you the pH of that midpoint. We're going to be doing lots of problems where we're going to be figuring out species, and we're not going to be calculating concentrations along the diprotic, triprotic ones, but like I said, I showed you if in a multiple choice question or a free response question, if they gave you a point, you should be able to identify which species is the most abundant at that point. Any questions? Now we're going to start the fun calculations. Yes?
I don't know if it's the diagram or if we did this on purpose. Is the slope for the equivalence point getting less, or getting essentially smaller and smaller as it becomes like more reactions over time? Because diprotic had a really steep slope, and triprotic has a less steep slope.
Well, I think generally, that is a good question. Generally, overall, what you'll see for a weak, strong combination, the buffer region, on the strong one, you have a definite like flat, and then all of a sudden it goes up, and then it goes like that. So there isn't a whole lot of slope. It's usually pretty flat, and then all of a sudden it goes right up. On the weak ones, the buffer region, like this area is more slopey. And it like as a kind of slowly increases, and that's because it's a buffer region, and we have the 2 buffer components in there controlling the pH. And yes, there should be an inflection that goes up, but it might not be as dramatic and as steep as you would see in a strong, strong combination. But that buffer region is going to be a little bit more of a slope as opposed to like a flat line. All right, so now we're going to calculate along different points of the titration curve. And we're going to start with a strong-strong combination, which is the easier of the two because it's really just stoichiometry and solution math that we did back in Unit 1. And it'll be probably, you're rusty on it and you'll need some review, but we're going to go over that. And for the strong, really it's just the moles equal the moles, so you have, you know, 1 mole of H plus 1 mole of OH gives you 1 mole of water. You don't have to worry about any other things occurring because if it's strong, the cation of the base and the anion of the acid are going to form a neutral salt that will not cause any secondary reactions in there. So it's very simple. All you're doing is H plus OH gives you water. Calculating the moles at the equivalence point, that's why the pH is always 7 too, because you have no secondary reactions in there occurring. It's a 1-to-1 ratio, and really it's more like limiting excess. You calculate the moles of each, subtract them, which one do you have more of? That one's in excess, that one's going to be driving the pH at that particular part of the curve. So in general, I put a curve on here so you can kind of see what we're going to be doing. We're going to start out, you know, here at 0. 0 is always the first one. You calculate the pH at 0. But then you're going to like do a calculation, you know, at about 10. Figure out the pH there. And then you'll do, what, another calculation at like 20. And usually they'll ask for a calculation at the equivalence point here too. And usually you have to find out the volume. You have to figure that out. The equivalence point, though, for a strong is very easy. You don't really have to calculate it because what is it always going to be? It's always going to be 7. Why? Because the products are the water and the neutral salt, so that neutral salt's not reacting with water or causing the pH to change. So that's what we're doing is as we're going along here, we're going to be calculating at those different intervals along the curve. So have a visual idea of where we're, you know, spacing out our calculations. So starting here with 0 milliliters, we have strong acid hydrochloric, 0.2 molar. We have strong base, 0.15 hydroxide. So calculate the pH after each volume of sodium hydroxide has been added. And originally in our flask, we have 10 milliliters of the hydrochloric to start with. Then you're going to slowly add the hydroxide. That's what's going to be in the buret. And of course, look for the calculation change. So at 0, what do we have in the solution? What's actually in the flask or beaker at that point? 10 milliliters of HCl. So if I'm looking there, I need to figure out to figure out the pH. What do we need? pH equals the negative log of hydrogen, you know, or hydronium, whichever way you want to look at it. Either or is fine with me. How do I figure out that amount when I'm dealing with a strong acid? The hydrogen concentration with a strong acid should equal its original acid concentration. Why is that? Because it completely dissociates. So in this case, we're going to say it completely ionizes like 99.999 whatever percent. But we're going to say that it completely ionizes. All we have to do then is what? Negative log of the 0.2. And what do we get there? Good. We're going to carry it out 3 decimal places. Why? Yes, we have the 3 significant figures in our concentration. Very good. So we carried out 3 decimal places. Very easy. Realizing since it's strong, the hydrogen equals the acid there. No problem. Now at 10 milliliters. 10 milliliters. So I like to write it out so you kind of have an idea what's going on here. Organizing all of the information. So you could write it as HCl, or you can write it as sodium hydroxide, but does the sodium and the chloride really matter here? No, they're not reacting, they're neutral salt, they're spectators, they're not doing anything. So I'm going to leave them out. We have 0.2 molar of this, 0.15 molar of the hydroxide, and how much did we add? 10 milliliters we have of the acid to start with, and then we added 10 of the hydroxide. So if we think about this, then this is really just, if we look at those numbers, which one's in excess? The hydrogen's going to be in excess here, because you can basically tell with 10 and 10, the one with the lower concentrations is going to run out. So what we need to do though is in order to figure out pH, don't forget the overall equation that we need this hydrogen here. We need to know what's the concentration of that hydrogen. So we have to recalculate the concentration of the hydrogen at this point. The first thing we need to do though, remember, molarity is moles over liters. No, because it's neutralizing. This is reacting with that to produce water. So what we need to figure out is how many moles of hydrogen is still around. And since we have 10 milliliters of the acid, we added 10 milliliters of the base to it, what do we have? We have a new volume of 20 milliliters. So we have to recalculate the molarity at this point. So let's go ahead and do that. So let's start with the acid. So there's my H plus for my hydroxide here. So as you can see, this is really just starting to look a lot like Unit 1 solution stoich. So then all I have to do is subtract them. What do we get? What's left over? Very small amount of hydrogen, but that's just the moles. Then we need to do the what? So the 10 milliliters plus the 10 milliliters gives us the new volume. So new volume, don't forget to do that step. That'll throw off your concentration if you don't do that step. So that's 20 milliliters. So we divide this by 0.0200 liters. And what do we get for our concentration? So molar of the hydrogen, then what do we do? Negative log of that value, and our pH equals, good, 1.602. Now at the equivalence point, as we say, pH is always going to be 7. You don't have to really do a calculation here. No problem. Since it is strong, we have the neutral salt as one of the products. Always going to be 7. That's the easiest one. Now for the excess part, when we're at the top part of the curve where we've added extra hydroxide now. It's gone past the equivalence point. So there is now extra hydroxide floating around. So what's going to be driving the pH at this point is going to be the hydroxide. All of the H plus is gone. It is now turned into water. It is no longer in the solution anymore. So We have more OH. We need to find the new hydroxide concentration. Do the 14 minus the negative log of the hydroxide to get the pH at that point. So this ends up becoming basically an OH excess problem. So at 20 milliliters here, 20 milliliters of the sodium hydroxide has been added. We need to figure out how many moles of that hydroxide has been added at this point. So I'm going to start there. So we have 0.0200 liters, or 0.150 moles of the hydroxide equals 1 liter. So how many total moles of hydroxide have been added into the solution at this point? Zero, 3. Yes, no? Moles hydroxide, right? How much has been added at this point? Total hydroxide added. Now, if we recall back from like the 10 milliliter one, how many moles of acid were in there, the H plus to begin with? So I'm not going to make you recalculate that at this point. The 0.002, this was, we already calculated, that was the total moles of the hydrogen in the solution. Yeah, we got it from the previous problem. Now if we subtract these two, that's going to give us how many moles of hydroxide are left over? This is how many moles are left over. But once again, when we're using the we're doing the negative log equation, we need concentration. So we also have to figure out what? New volume. The new volume. So we have our 10 milliliters of our original acid, okay, plus the 20 milliliters of the base that was added. So that's a total of 30 milliliters in there. So we divide this by the 0.0300 liters. This is going to give us our concentration of hydroxide. Which ends up being
1.47.
you get 0.0333?
Yeah.
All right, good. Now, we're still not done, because what do we ultimately want? pH. So, 14 minus the negative log of 0.0333. This will give us our pH. So, what is the pH at this point? 12.523. Very good. Simple enough. Last part, when you're in the upper part of the curve, this is going to be an OH excess problem. Any questions? Because it's going to look different now for the weak strong combination. All the calculations except for the last one are different. At the end, you're always going to have a lot of extra OH, so that last calculation is going to be the same as this one. But now for the weak strong, it's going to look different. All right, good. Yay, we're correct. All right, now there's a space here for you to just kind of write down the methodology first. Then right below that is going to be the space to do the problem for the 0 milliliters. So I want you to first write down the methodology of each stage. Then we're going to start working the stages. Okay? So at the 0, if we are now dealing with a weak acid being titrated by a strong base, which we know this because looking up there, what's our acid? It's acetic acid, and we know acetic acid is a weak acid. So we know this is going to definitely be a weak one that we're dealing with. What's the other thing that pops out at you that kind of tells you it's weak? You have a Ka value given to you in the problem too. So that's another little thing that will pop out at you so you know that this is weak. So at 0 milliliters, when you haven't added any hydroxide, the only thing you have in solution that's been dumped in there is the acetic acid. So what is it doing? Acetic acid's reacting with water. So it's basically a weak acid equilibrium problem. Same thing as we've been doing in the previous, lesson. This is just, nothing's been added, so it's really just acetic acid with the water. A little bit of it reacts with water, you get a little bit of hydronium, you get a little bit of conjugate base. So that part we know how to do. We already know how to do it, it's just the beginning part. Second part, the 10 milliliters, puts us right in the middle of the buffer region of the curve. You don't know how to do this yet, but we're going to learn towards the end of the notes how to do this. Because you first of all have to define what a buffer is and the buffer components and all that. So we're going to learn this, not to worry, but we're going to skip it for now. At the equivalence point, what you got to remember, at the equivalence point, all of the acid has been neutralized by the base. All of the acid is gone. You've added enough so all of the HA is gone. What are you left with at the equivalence point? You are left with conjugate base floating around in the water. Nothing else is in there at the equivalence point. So guess what you have? A weak base equilibrium problem. And this is why the pH is above 7 at the equivalence point, because you have conjugate base in there reacting with water, driving up the pH a little bit. So that's what we're going to be doing at the equivalence point, is a weak base. Now it's a little bit more complicated because you got new volumes and all the stuff to recalculate the concentration. So you do know how to do a weak base equilibrium problem. We will, get into the amounts and how to find the new concentration with that particular problem. At the 20 milliliters, once again, you're on the upper end of the S curve there. So really, this is what we just did. It's going to still be an excess hydroxide problem, just like we did before. Yes, there will be a conjugate base in there, but that minute amount of conjugate base reaction does not drive the pH at this point. It is going to be primarily driven completely by the hydroxide extra, because it is much more strong, obviously. Okay, so we just did that problem. You know how to do the 20 milliliter part. So let's take a moment here, kind of think through the strategies, okay? And we're going to start working the problem here in just a second. So here, we're going to start now at the 0 milliliter mark, where we haven't added any hydroxide. It's just a weak acid equilibrium problem. It is something that you've already done. You'll recall it, hopefully. And at this point, I'm hoping that maybe you're past doing the rice tables. So at 0 milliliters, the question is, what is the pH of the 0.2 molar acetic acid? Now, you can write out the whole equation and the whole rice table. At this point, I don't think it's necessary to write out the whole rice table. But what I would like to see for your work is making sure that you write out the Ka expression. So, write out the Ka expression, what's going to be the products. Hydronium and acetate, good. So those are going to be our products. That's the conjugate base and hydronium, and what goes on the bottom? The acetic acid, the original acid. Now, if you still need to write out the reaction and set up the rice table, that is fine. If that helps you organize things, I'm okay with you still doing that. That's fine. But hopefully you've gotten the pattern down enough to where you can go straight to the expression. That means the Ka, 1.8 times 10 to the minus 5 should equal what? X times X on the top, right? Over 0.200 minus X, right? Yes, and let's get rid of X. Why can we get rid of X? Ka, 10 to the 5th. That's definitely going to be small enough. So we're going to, but write down here that you're using 5% rule.
Do we have to every time we get rid
You need to acknowledge the fact, it does show in the scoring guidelines that they want you to acknowledge that you realize it's too small. So you're eliminating X due to the 5% rule. Eliminate X. They do want to see that. They want to show that you know why you're doing that. And if you don't write that there and you keep the X in, then they're expecting to see the X value as if you were to graph it. So make sure that if you're going to take it out, you note that you're taking it out so that, you know, your X shouldn't be any different, but that has been, you know, noted there. Question?
Right.
Okay. All right. Now, let's calculate it. What do we get? X equals
0.0019.
good, 19 molar. And of course, X represents our hydronium here. It also represents the acetate. Don't forget that because they're both equal at that point. It's 1 to 1. And what do we need to do here with this value? Just negative log at this point. And what do we get? It's 2.72. Okay, so 2 sig figs in the molarity. We're basing that off of the 2 sig figs in the Ka. So we're going to go with 2 decimal places. 2 and 2. Yes?
Why did we go with 2 sig figs for the X?
Because this has got 2 right here. Base it off of the Ka. And yes, this would be correct. There you go.